Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of derivatives. The past 4 lectures have dealt with the problem of local extrema, which you can look at as the tops of the hills and the bottoms of the valleys of a function. Today in lecture 33, we talk about a related topic called absolute extrema, which you can look at as the highest peak on the graph of your function or the lowest valley. Our goal is this. Given a function f, we want to find an x that makes f of x as large as it can possibly get. In other words, x maximizes f of x. And also to find an x that makes f of x as small as it can possibly get, that minimizes f of x. I'll illustrate this with a picture. Here's a function f defined for positive real numbers. That's its domain, positive real numbers. And you can see that it has a local maximum here, another local maximum here, and a local minimum here. But imagine you wanted to find a value of x that makes f as big as it can possibly get. Well, you can see that right here at this local maximum, that's also a maximum for f. That's as big as f could possibly get. So at this number c, f of x attains its largest value here. So beginning today, we'll be interested in numbers c like this that maximize f, and also those that minimize f. What if we wanted to find an x that makes f as small as it can possibly get? Well, we have a local minimum right here, but f could get smaller than that. For example, way over here, it's as low as 0. f of 0 equals 0. So f attains its smallest value right here. And notice that's not even a critical point. So what we'll deal with today is, as you can see, a little bit different from local extrema. The highest point and the lowest point on your graph, those are what are called absolute extrema. And that's today's topic. For example, if you had a function that gave you profit in some manufacturing situation, you'd want to find the x that maximizes that. If c of x represented cost, you'd want to find a value of x that minimizes that. The basic theme is to maximize good and to minimize bad. That's what we're all about in today's lecture. We'll start with some big definitions, ones that will be with us for this chapter. Suppose f of x is a function that's defined on some domain. So D is the domain of that function. Usually that domain is an interval. It might be an open interval or a closed interval, or it might be the whole real numbers, the interval from negative infinity to infinity. We say that f of x has an absolute maximum at a number x equals c if f of c is greater than or equal to f of x for all x in that domain D. So, for example, here is a graph of a function y equals f of x. And it's defined on this domain D here that's just a closed interval from this point to that point. Now, you'll notice that at this particular value c, you get f of c way up there. It's higher than any other point on the graph of this function. For any other x you pick, f of x will be here. You get f of c greater than or equal to f of x for any other x in this domain. F of c is greater than f of x. And according to our definition, that would mean that this function f of x has an absolute maximum at x equals c, because f of c is greater than or equal to f of x for all x in D. Here's a new definition. We say f of x has an absolute minimum at x equals d, little d, if f of little d is less than or equal to f of x for all x in d. Almost exactly the same as what came before, but we're switching the greater than or equal to a less than or equal to and changing maximum to minimum. In this picture, here's a value of d, and its corresponding f of d, and that point is lower than any other point on the graph of this function, on this domain d. F of d is less than or equal to f of x for any x in this domain. And so we would say that f of x has an absolute minimum at x equals d, because f of d is less than or equal to f of x for all x in d. New example. Slightly different function. I've got the same domain D here, but the function has changed a little bit. You'll notice that here's a C that has an absolute maximum right there. That's as high as you can get on this graph. And there's another point C over here that gives you that exact same maximum. So f of x has an absolute maximum at x equals C, either this C or that C, because for either one, f of c is greater than or equal to f of x for all x in d. So the point here is that you could have an absolute maximum of f of c, one maximum, that could occur at several x values here and here. Likewise, notice that f of d, where d is this endpoint, that's as low as you can get on this graph. So f of x has an absolute minimum at x equals d, because f of d is less than or equal to f of x for all x in d. You can see here's f of d, and there's an f of x. You fiddle around with x and you change it, that f of x is going to go up and down, but it's always going to be that f of d is less than or equal to f of x for x in this interval. Some terminology. We say that f of x has an absolute maximum at x equals, that if f of x has an absolute maximum at x equals c, then the y value f of c is the absolute maximum of f of x at x equals c. So the absolute maximum is a y value f of c, and it occurs at an x value c. And you can see that here. X value c gives you a maximum of f of c. Likewise, we say f of x has an absolute minimum at a number x equals d, or if f of x has an absolute minimum at x equals d, then f of x is an absolute minimum of f of x at d. So here, f of d is an absolute minimum. It's a y value, but it occurs at an x value d. And we say that f of c and f of d, these two y values that are maximum and minimum, they are called absolute extrema of f of x on d. A few other examples. Here's a graph of an f of x. It's a parabola. The domain d here is the interval from negative infinity to infinity, so it's the whole real number line. So it's an infinitely big graph, and that's what the arrows mean. We have an absolute minimum at the y value of -1, and that happens at x equals 1. Notice that in this example, there is no absolute max. Whatever c you pick, and you look at f of c, you can always go higher than that on this graph. So there's no way to get to a highest point. There is no highest point. It just goes to infinity. So no absolute maximum. Now here's another example. It's exactly the same f of x, except we're using a different domain d. Instead of the whole real number line, the domain is the closed interval from -2 to 3. From -2 to 3. And we're just looking at the graph on that domain. Now we've got the same old absolute minimum from before of -1 that happens at x equals 1. But notice we now have an absolute maximum. At -2, which is in this interval, f of that, that's as high as you can get on the graph. F of 2 is 4. So we have an absolute maximum of y equals 4 and x equals minus 2. Another example. Here d is the entire real line again. And this looks like a cube function. Notice here there's no absolute maximum and there's no absolute minimum. You can keep going down and down and down. You never get to a lowest point, nor do you ever get to a highest point on this graph. More examples. Here we have a linear function on the closed interval from -2 to 2. Oh, this is easy. You can see right there you have an absolute minimum at x equals minus 2. That's as low as you get. And you have an absolute maximum at x equals positive 2. That's as high as you get. This is almost the same function, but notice I've changed the interval just slightly. I've made it an open interval, or a half-open interval. It's open at -2. So the point -2 is not included in that interval. So you have a little white dot there and a corresponding white dot up there on the graph. I want to call to your attention that for this particular domain D, this function has no absolute minimum. You want to say the minimum occurs right there at x equals minus 2, but that's not in the domain. If you take a c in the domain, it's going to be a little bigger than minus 2, maybe, and f of c will be up here on the line. You can always go smaller than that by getting your c closer to minus 2. So you can't attain an absolute minimum on this interval because the point where the minimum should be is not in the interval. That -2, you can't plug that into the function because it's not in the domain. But we have an absolute maximum at x equals 2. That should be pretty clear. That's as big as you can get. And 2 is in that half-closed interval. And then next, change that interval just a little bit, knock off that other right-hand endpoint. Now it's an open interval from -2 to 2. Here, f has no absolute minimum, and it has no absolute maximum. You want to say the maximum occurs right there at x equals 2, but that's not in the domain. You can't plug in that x equals 2. So there's no absolute maximum here. If you took a c just less than 2 and looked at f of c, you could always go higher than that by moving closer to 2. So these examples serve to illustrate a really important point that extrema can depend on the interval d on which f of x is defined. And we see that happening throughout the examples on this slide. The takeaway from these examples is this. To find the absolute extrema of f on a closed interval, we know where to look, at critical points and at endpoints. So here's a function on a closed interval from a to b. It has an absolute minimum at this critical point c and an absolute maximum at this endpoint b. So in finding the absolute extrema of f on a closed interval, we can just find the critical points, plug them into the function, and then plug in the endpoints, and take the biggest one of those, and that's your absolute maximum, and the smallest is your absolute minimum. But things are not going to be so simple if the interval is not closed. Imagine this function f was defined, instead of on the closed interval from a to b, the open interval. You may not know exactly what happens at the endpoints. At this endpoint b, does the function go up higher than this local maximum, or does it level out like that? At this endpoint a, does the function dip down lower than this local minimum, or does it not? It's not quite as clear-cut. So today we're going to do two things related to these two observations. First of all, concerning this first picture, we're going to develop a procedure for finding absolute extrema on a closed interval, and we'll look at some examples. Next, we'll address this situation. We'll discuss finding absolute extrema on a non-closed interval, and we'll look at examples of that. So let's concern ourselves, first of all, then, with absolute extrema on closed intervals. In this situation, there's a theorem that applies, which you'll read about in your textbook. It's called the extreme value theorem. And it states something that it should be pretty obvious. It's very intuitive. If a function f is continuous on a closed interval from a to b, then it has both an absolute maximum and an absolute minimum on that closed interval. So the picture is this. You've got a f of x defined on a closed interval from a to b, and you can imagine this physically as a piece of bent wire on a piece of paper, and imagine a straight edge, say a metal straight edge that's horizontal up here, and you lower it down, and at some point metal will hit metal with a click, and that's your highest point on the graph. Taking that straight edge on the bottom, it's horizontal, just raise it up higher and higher and higher, and at some point, click, metal will hit metal, and that's your absolute minimum. So this theorem just tells you that you're guaranteed to have an absolute maximum and an absolute minimum when f is continuous on a closed interval. And that's useful because if you're trying to find absolute max and min, when you start out, it's good to know that they actually exist. And this theorem is going to tell you that they exist if f is continuous on a closed interval. This theorem should be really obvious, but it's interesting because if you look at a proof of it, the proof actually becomes very subtle. The truth of this theorem relies on some very intricate properties of the real number system. And it's not something that we can tackle in this course. If you ever take a course in advanced calculus, you'll prove this extreme value theorem. For us in this course, we'll look at it as something that's just intuitively obvious and use it freely. I do want to point out in the setup of the extreme value theorem, f is continuous. If f is continuous on this closed interval, then you've got an absolute maximum and an absolute minimum. I want to point out that continuity is very important. It's essential. For example, here's a discontinuous function f defined on a closed interval, and I want to point out that it has no extrema at all. You want to say that it has an absolute maximum right here, that's the highest point at this c, but no, f of c is right here. That's not an absolute maximum. And you want to say it has an absolute minimum, also at c, because you could be way down here. But no, if you plug in c, you don't get a minimum. You could get values of x that are really close to c, like right here, but that's not an absolute minimum because you could move in a little bit closer to c and go lower. This function has no extrema at all. So you can see how significant continuity is here. Okay, with that, we can state our procedure to find all the absolute extrema of f of x on a closed interval from a to b. Now notice by the extreme value theorem, we know that the absolute maximum and absolute minimum exist if f is continuous on a closed interval. And in calculus, we're talking about functions that have derivatives, so they're going to be continuous. Here's our procedure. In the first step, you find all the critical points c of your function f that are in that closed interval. And remember that you could have a minimum or a maximum at a critical point. So it's important to find those. In the second step, you're going to compute f of a the left-hand endpoint, and f of b, f of the right-hand endpoint, and also f of c for each critical point c that's in the interval that you got in step 1. And doing this, you'll get a bunch of numbers, at least 2 numbers, f of a and f of b, and also maybe 1 or more f of c values. Just as in our examples, the largest value from step 2 is your absolute maximum, and your smallest value from step 2 is your absolute minimum. So this is the procedure that we're going to use to find the absolute extrema of f whenever it's defined on a closed interval. The interval has to be closed for this to work, so you can plug in the endpoints. Let's look at an example. Here we will find the absolute extrema of the function f of x equals the cube root of x squared minus 4/3 x on the closed interval from 0 to 27. And think about the procedure from the previous page. So our procedure says that we should, first of all, in step 1, find all of the critical points of f of x that are in the interval. Now, remember what a critical point is. It's a value of x that makes the derivative undefined or equal to 0. And if you're looking for those critical points, you have to take the derivative. You want to find out where that derivative is either undefined or equal to 0. So take that derivative. Now I'm leaving out the details here because I think you know how to take the derivative of this function. So f prime of x, when you work it out, turns out to be 2 over 3 cube root of x minus 4/3. So we're looking for the values of x that make that undefined or equal to 0. Those are our critical points. And from this, you can see that just looking at the function, just by inspection, you can't plug a 0 into that because you'd be dividing by 0 right here. You can see that f prime of 0 is not defined, and that makes x equals 0 a critical point. Now, I should mention that even though x equals 0 is a critical point of this function, notice that that also happens to be an endpoint. So it's both an endpoint and a critical point. This happens sometimes. For every other value of x, you're not dividing by 0, so you're not going to get any other critical points where the derivative is not defined. But you might get some critical points where the derivative is equal to 0. So to find the other critical points, we must solve the equation f prime of x equal to 0. So in solving this, we'll find all the values of x that make f prime equal to 0, and those are going to be critical points. So we computed our f prime up here, so f prime of x equal to 0 would be this expression equals 0. And we're solving for x, which only occurs in one place. Let's start to isolate it. We could scoot that negative 4/3 over to the other side as a positive 4/3. And then we can cross multiply. We get 12 cube root of x equals 6. We could then divide both sides by 12. Cube root of x equals 1/2. And at this point, we just cube both sides of that to get x equals 1/2 cubed, which is 1/8. So the value x equals 1/8 is the only number that we got in this solution. So it's the only number that makes f prime of x equal to 0. F prime of 1/8 equals 0. So in summary, our critical points are x equals 0 and x equals 1/8. Okay, all of this was step 1 of the procedure on the previous slide. We found our critical points that are in our closed interval. Step 2 asked us to plug in the endpoints of the interval and those critical points. Well, as I said, x equals 0 is both an endpoint and a critical point. We've got to plug it into the function. F of 0 is the cube root of 0 squared minus 4/3 times 0, and that's 0. We also have to compute f of the other endpoint, f of 27 is the cube root of 27 squared minus 4/3 times 27, which gives us negative 27. Notice at this point we're taking our critical points and endpoints and plugging them into, not the derivative, but actually f. We're interested in f. What's its maximum and what's its minimum? Let's see, there's one other thing we got to plug in. We got to plug in that critical point. And again, we're plugging that critical point into f. You know, if we plugged the critical point into 1/8 into f prime, you're going to get 0. Okay, we're interested in f here. What's its maximum or minimum? F of 1/8, well, if you work that out, plug in the 1/8 into f of x, and work it out, you get 1/12. I'll give you a moment to kind of look at that. Convince yourself that you do get 1/12. I had to get a common denominator right here. There's 1/12. Now, in step 3, you look for the largest and the smallest values that you see here, and those are going to be your maximum and minimum. Now, if you look at this, you got 0, minus 27, and 1/12. 1/12 is the only one that's positive, so that's your maximum. So your absolute maximum is 1/12 at x equals 1/8. And what's the smallest value you get? Well, it's not the 0 because you go way down there to negative 27. So your absolute minimum is negative 27, and it happens at x equals 27. You plug in 27, you get negative 27. And that answers our question. We found the absolute maximum and the absolute minimum of our f of x on the interval from 0 to 27. Now, that's an answer, but I want to give you a little bit of background here. Just, you don't have to do this, but I've sketched a really rough sketch of the graph of this function. I've got the interval from 0 to 27. What the function does is this. It starts out at x equals 0. It reaches a high point right there at x equals 1/8, and it starts going down. And by the time you get to x equals 27, it's down here at a y value of negative 27. Obviously, this graph is not to scale, but it gives you a sense of what's happening with this particular f and what your extrema look like. Let's do one more example. Now again, in this example, we want to find the absolute maximum and the absolute minimum, in other words, the absolute extrema of a certain function. And here the function, in this example, is f of x equals x times sine of x minus cosine x plus cosine x plus sine of x. And we want to do this on the interval from pi over 2 to pi. So again, we're going to go through our 3-step procedure that we outlined a couple of slides ago. The first step is to find the critical points of your function, f. Now remember, the critical points of f, those are the values of x that make f either undefined or equal to 0. The critical points of f are the values of x that make the derivative either undefined or equal to 0. To find those critical points that make the derivative undefined or equal to 0, you first of all have to find the derivative of the function, f prime of x. And here it is. Okay, if you look at f of x up here, the first term is a product plus these other two terms. So you've got to use the product rule first on this part. So you get the derivative of x times sine x minus cosine x plus x times the derivative of sine of x minus cosine of x, which is cosine of x plus sine of x. And then you have minus the derivative of cosine x, which is minus sine x, and then you have the derivative of cosine x, which is minus sine x, and then the derivative of sine x, which is cosine x. So there's our derivative f prime, and I promised you when we are taking derivatives in this section, we'll need to simplify them, and we're doing that here. Notice you get a 1 times of sine of x minus the sine of x, that goes away, and a negative cosine x plus cosine x, that goes away too. All you're left with is an x times cosine of x plus sine of x. Now, you'll notice that this is defined for all values of x, No matter what x is, you can plug it into the derivative and get a meaningful value here. There's no denominator that's going to turn into 0 or anything like that. So you're not going to get any critical point C for which f prime of C is not defined. There are just no such critical points. But you might get some critical points C where f prime of C is equal to 0. Let's see if we can find those. To find those other critical points, we've got to solve this equation, f prime of x equals 0. Okay. Well, here's our f prime of x worked out and set it equal to 0, and we've got to solve this. Now, it's in factored form. You have an x times this other expression, and in order for this whole thing to equal 0, either the x has to be 0 or the cosine x plus sine x has to be 0. So either x equals 0 or cosine x plus sine x is equal to 0, one or the other. And right away, that gives us a solution to the equation. X equals 0. That's a solution. It makes this derivative equal to 0. To find the other solutions, we have to look at the values of x for which cosine x plus sine x is equal to 0. Now here's where the unit circle is going to come into play. We're basically solving a trigonometric function here, or trigonometric equation here, cosine x plus sine of x equals 0. And remember, we're on the interval from pi over 2 to pi. On the unit circle, here's pi over 2, and there's pi, so x is a radian value since it's plugged into trig functions. X is between pi over 2 and pi. And we're looking for what x makes cosine x plus sine x equal to 0. And if you think about it, there it is right there. X equals 3 pi over 4, which is, that's what, 4 times 45 degrees, 4 times pi, or 3 times 45 degrees, 3 times pi over 4. It's like a 45, 45, 90 triangle right there, where the two legs of that triangle are equal. This one at the horizontal one is cosine of 3 pi over 4. That's negative square root of 2 over 2. And the vertical side is sine of 3 pi over 4. From the triangle, we see that's positive square root of 2 over 2. And that negative and positive, they're equal values, and they cancel out here and give us 0. So the only x in the interval from pi over 2 to pi for which cosine of x plus sine of x equals 0 is x equals 3 pi over 4. Therefore, the only critical points we're picking up here are x equals 0 and x equals 3 pi over 4. But watch out, be real careful, and don't get on automatic pilot, because that x equals 0 that we picked up as a critical point, it's not even in our interval. And remember, the procedure said to find all the critical points that are in that interval. We're not interested in other points, only what's in that interval. So the only critical point we're picking up in step 1 is x equals 3 pi over 4. Okay, let's move on to step 2. In step 2, you plug in your endpoints and all of your critical points from step 1. There's only one critical point. Okay, let's start with our endpoints. We've got an endpoint on the interval of pi over 2. We do f of pi over 2. We're plugging that into f. Not f prime, but f. Here's f up here, that whole function. So f of pi over 2 is pi over 2 times the quantity sine pi over 2 minus cosine pi over 2, plus a cosine pi over 2 and a sine pi over 2. Well, cosine pi over 2 is 0 and sine pi over 2 is 1. When you run that through, you get pi over 2 times 1 minus 0 plus 0 plus 1. So f of pi over 2 is pi over 2 plus 1, which is approximately 2.57 if you take out a calculator or do it by hand. And then we do f of our critical point, which was 3 pi over 4. F of 3 pi over 4, it's worked out here. Same calculation we did before, we just plug it in 3 pi over 4. Well, sine, typo, that should be a 3 pi over 4, sorry about that.
Sine of 3 pi over 4 is positive root 2 over 2. Cosine 3 pi over 4 is negative root 2 over 2. So these guys cancel out. These guys add together. And that works out to be 3 pi over 4 square root of 2, which is about 3.3, if you take the time to work it out. And finally, we have to do f of this endpoint pi. Oh, this is refreshingly easy. It's pi times sine of pi minus cosine pi plus sine pi. Well, cosine pi is negative 1, and sine of pi is 0. So you work all that out. You get pi minus 1. It's about, well, pi is 3.14 approximately, so pi minus 1 is going to be 2.14. So our procedure says that we can find our maximum or minimum by looking at the largest value that we got here. That's going to be our absolute maximum, and the smallest value is going to be our absolute minimum. Let's see. Looks like our maximum is the 3 pi over 4 root 2, which is about 3.3. That's bigger than these other two values. And here's our minimum, pi minus 1. That's the smallest of these three values. So in conclusion, the absolute maximum, it's 3 pi over 4 root 2, and it happens at x equals 3 pi over 4. Our absolute minimum is this pi minus 1, and it happens at x equals pi. And there we go. We've solved our problem, and we've attained the goal that we set out to attain at the beginning of the lecture, at least when we're talking about a closed interval, a function on a closed interval, like in the previous two examples. We have a procedure that finds the maximum and minimum values of those functions.
In the examples that we just looked at, we used our procedure for finding the absolute extrema of a function on a closed interval. But what about the extrema on a non-closed interval? We don't yet have a way to find the absolute extrema of a function on, say, an open interval. We mentioned earlier today that in general this can be tricky. If your function is defined on an open interval, it may not be defined at the endpoints. And if you can't plug in b in this picture, you don't know necessarily whether or not you have an absolute maximum at this c or not. You don't know whether the function goes higher than that. If you can't plug in a, you don't know whether or not you have an absolute minimum here. Does the function get lower than that? It's hard to tell. However, fortunately, there is one situation in which it's easy to make a definite conclusion. And fortunately, that one situation applies very, very often. And I'm going to state it in a theorem. It's this. Suppose f is continuous on an interval, and f has only one local extremum on that interval at a number c. So here we're talking about local extrema, not absolute extrema. F only has one local extremum on this interval. And the theorem says this. It comes in two statements. The first statement is this. If f of c happens to be a local maximum, then it's also an absolute maximum. And you can see why that has to be the case very easily. Because imagine that you've got this set up and f of c is a local maximum. Say it's right there. F of c is a local maximum. And as stated here, it's the only local extremum of this function on the interval. And the theorem is claiming that that local maximum is an absolute maximum. And here's why that has to be the case. What if it wasn't an absolute maximum? Well, then you could get higher on the graph. but it's already a local maximum, so either way you move, you're going lower. So moving to the right, maybe you could get to a higher point. So you first go lower, and then imagine it did happen that you could go higher over here. Well, somewhere that function would have to turn around, and you'd pick up a local minimum. But it's stated here that you only have one local extremum on the interval. That's your assumption. So that's why if f of c is a local maximum, then it has to be an absolute maximum. And by the exact kind of reasoning, if f of c is a local minimum, then it's also an absolute minimum. So this theorem is really useful. It gives a way of finding the absolute extrema of a function on an interval, either open or closed, under this situation where there's only one local extremum. So what this is saying is that if you're after absolute extrema and this situation holds, then you can use your techniques for finding local extrema to figure out whether you have and where you have an absolute maximum or an absolute minimum. Let's look at an example of that. Let's find the absolute extrema of the function f of x equals e to the x squared minus 5x plus 6 on the open interval from 0 to 4. So it's not a closed interval, it's an open interval. So our theorem holds for situations in which a function has only one local extremum on the interval of concern. So our strategy is going to be this. We're going to look for local extrema of this function on that interval, and we're going to hope there's only one of them. And if there is only one of them, we can use our new theorem. So let's carry out that strategy. If we're looking for local extrema, we've got to find critical points. And that means taking the derivative. F of x is e to the power of x squared minus 5x plus 6. So by the chain rule, f prime is e to the x squared minus 5x plus 6 times the derivative of x squared minus 5x plus 6, which is 2x minus 5. And to find the critical points, you're going to set that equal to 0 and solve. Now, e to any power, that's positive. It's never going to be 0. It's never going to be negative. So the only way that this derivative could be equal to 0 is if 2x minus 5 were 0. And that can only happen when x is 5 halves. So we only get one critical point, x equals 5 halves, and it happens to be in this interval. So our theorem is going to apply here. We've got a function on an interval, and there's only one critical point there. So all we need to do is figure out whether at that critical point of 5 halves we have a local maximum or a local minimum. If it's a local maximum, the theorem says it's an absolute maximum. If it's a local minimum, the theorem says it's an absolute minimum. To figure out which we have, let's think about the sign of f prime. We got two intervals, and for the right-hand interval, when x is bigger than 5 halves, f prime of that would be this positive number times 2 times a number bigger than 5 halves minus 5, and that's positive. Whereas if x is to the left of 5 halves, we're negative. So the function y equals f of x, therefore, by the first derivative test, has a local minimum right there at 5 halves. Our theorem then asserts that that local minimum is an absolute minimum. So answer, f has an absolute minimum at x equals 5 halves. And there's no absolute maximum. This function to the right of 5 halves just keeps getting bigger and bigger and bigger. And the same on the other side. So there's no absolute maximum, just an absolute minimum. That's it. Let's recap what we've learned today. We've found out how to find all absolute extrema of a function on a closed interval from a to b, and the procedure is this: find all the critical points c of f in that interval, then compute f of each of the endpoints, and also f of c for each c in step 1. And then from those numbers obtained in step 2, the largest value is the absolute maximum, and the smallest value is your absolute minimum. So that's our procedure for finding absolute extrema on a closed interval. For open intervals, it's a little more tricky, but we have this great theorem that's going to apply very often. Suppose f is continuous on an interval, and f has only one local extremum on that interval at c. If f of c is a local maximum, then it's an absolute maximum. If f of c is a local minimum, then it's an absolute minimum. These two procedures are going to be very useful for us in the next lecture. What we're going to do there is to apply the knowledge that we've obtained thus far in part 4 of the course to practical problems. We'll put it to use. So I'll see you there, and goodbye.